Hello, everyone. Welcome to this video brought to you by the Steel Tube Institute. My name is Kathleen Jacinto, and I am a structural engineer and a technical consultant to STI. Today, we will discuss how to design moment connections from joists to HSS columns. HSS is structurally efficient in a few different ways. Because of its high radius of gyration, it does great in compression, so it makes it a good choice for columns for both short or tall unbraced lengths, as shown in one of the examples here at the SeaTac Airport in Seattle. For this reason, we often find ourselves connecting to HSS columns. We might have Y-flange beams, HSS beams, or joist girders to HSS columns. We'll look at joist girder to HSS column moment connections in this video, and we'll specifically explore a top plate joist connection to the HSS column in order to transfer our moment and our shear. So this video will show standard steel bar joists to HSS columns. However, there is the potential for the use of joists utilizing HSS as the top chord, bottom chord, and diagonal web members of that joist. If you happen to be designing an HSS joist, then this top plate connection may also be an option to transfer moment through that HSS joist to the HSS column connection. But today we'll be focusing on typical bar joist girder to HSS column connections as shown in this detail. So we can see here that our joist has moment and that results in a force couple in the top and bottom chords of that joist. That top chord force will be transferred to the column by using a top plate field welded to the joist girder top chord and to the HSS column cap plate. If you have joist girders framing into both sides of the column, as we show here, then the top plate is also used to transfer continuity forces from one joist girder to the other. For that bottom chord force, we have a stabilizer plate to transfer that force to the HSS column. And then for the shear reaction R that we see at the joist top chord, we have a stiffened seated connection to the HSS column. As you can imagine, there are several limit states to check for this connection, including checks on the plates and the welds. But for this video, we will focus on limit states specific to the HSS column, and I will point you to resources for designing all the connecting elements at the end of the video. We'll be using AISC 360-2022 specification as our basis, with its companion 16th edition AISC manual. So first, we're going to look at the top plate part of this connection. As we saw in that image, the moment in the joist is broken down into a force couple at the top and bottom chords of that joist. This results in a top chord imposing a shear force that's transferred to the top plate and to the top of the HSS column. The first check that we're going to take a look at is shear yielding of the HSS column due to that top chord force. We turn to AISC specification chapter G, equation G4-1 as shown here, and we can go ahead and plug in A sub W and C sub V2. If you have a square or rectangular HSS column, we need to make sure that we're considering the workable flat of that HSS column, neglecting the corner radius in that equation for H. If you find that we don't have adequate capacity, then there are two routes that we can go. We can select an HSS column with a thicker wall. That would be the preferred method to save the project money. Or we can provide an HSS column with longer walls to transfer that shear. But this all assumes that we are thinking about the connections while we still have the members in design and before they've gone out for bid or for a mill order. But if you happen to not be the EOR and say you're the delegated connection designer and we don't have control any longer on the member thickness before bid, then we might have to reinforce that wall to make that shear yielding check work, which could be more costly than upsizing that column. So it's important to think about the connections during member design in order to avoid that need to reinforce the column or to upsize that column after bid. When we're doing our weld design, we also need to keep in mind that the welds from the cap plate to our square or rectangular HSS column needs to consider the workable flat dimension as the weld length that is available to us for the weld. So we can't use the full out-to-out nominal dimension. It's a slightly reduced length that's shown in that equation at the bottom of the screen that for neglecting the contribution of the corner radius. Before we dive in further into all the limit state checks that we need to make on our HSS column, I'd like to point you to this resource. STI developed limit state tables to summarize the limit state equations to consider. There are 4 different tables separated by type of loading. We have shear, axial, truss, and moment. And each of these tables has several HSS connection types to select from. The equations to check are based on AISC 360-2010 as well as 2016 and are summarized on these tables that are free to download on the STI website at the link below. So now we're going to design for that vertical shear reaction due to the joist to the HSS column. That shear is shown as R in the image on the right and is transferred through the stiffened seat connection at the top chord of the joist. There are actually 2 different limit state tables that can be used to design this stiffened seat connection. So the STI shear table, we can refer to the stiffened seat connection. And then the moment table, we turn to the branch under in-plane bending. And that's because we'll end up having a moment that results from the R shear reaction that occurs at an eccentricity to the HSS column face. So our first check will be to check the maximum wall slenderness on that HSS column. We have a B/T ratio to check per the ASC specification table B4.1b, and I show that we need to check case 17 for this check. Next, we need to consider the eccentricity of that shear load. And when we turn to the 16th edition manual, page 10-39 under the stiffened seated connection section of part 10, then we see that we need to consider an eccentricity equal to 0.8 W, with W in our condition being W sub S, the width of our stiffened seated connection. When we want to design the thickness of that vertical stiffener plate, we need to check for punching shear of the HSS. So we turn to equation 10-10A of the 16th edition manual. This equation, as we see, is not in the specification. There used to be a version of this punching shear equation in the 2010 specification. It was equation K1-3 of that spec. Then in the 2016 code, it was moved into the manual, part 10, where it remains now in the 2022 specification. And some background on that is that Dr. Don Sherman had conducted research on shear tab connections with 3 or 4, sometimes 5 bolts. However, we were using that equation for other applications outside of what was tested. So the specification committee voted to take that equation out of the spec, and it's now in the manual, and we've also added in effects of eccentricity into that equation. So this is the equation that we currently need to check for our maximum plate thickness for punching shear. One note is that since our seated connection is located at the end of the HSS column where we have our top plate running over, we need to take a reduction due to connection end distance. And for this limit state, we would need to take a 50% reduction. Since we have a plate, which is considered a branch member, imposing moment onto our HSS column due to that eccentric shear force, we look at the STI moment limit state table. And there we see that we need to do another check for shear yielding or punching due to an in-plane moment. You can see here on the image on the right that we have the horizontal member shown in this image is essentially our HSS chord or column. And this image shows HSS branch members, but for our condition, we have our stiffener plate, which could be substituted for that branch member. Dr. Jeff Packer from the University of Toronto wrote an STI article on HSS connections under branches in plane bending. So that article points us to check for punching using equation 2 of that article shown here. And we need to assume an effective width B sub EP. That equation is also shown. Our H sub B will be the vertical length of our stiffener plate, or L sub S, in our connection detail. And then our B sub B is substituted as the thickness of our stiffener plate. And again, we need to take a reduction due to connection end distance. The next limit state that we're going to look at is wall plastification of the HSS column. So this is due to the vertical stiffener plate attaching to the HSS connecting face, which ends up acting like a flat plate, as you can kind of see here on the image on the right. So we have our HSS connecting face that is a flat plate spanning to the HSS sidewall supports. And that plate is bending in its weak axis. And while it's bending, it forms yield lines as shown on that image. So we're essentially checking the flexural capacity, or the plastification capacity, of that HSS wall. We use equation 9-46 out of the 16th edition manual, and we substitute the variables as shown here, where L is equal to the vertical length of the stiffener plate and C is the thickness of the stiffener plate. We have to account for a Q sub F factor that's shown in that equation 9-46. We need to make sure and take into account, when we're designing that connection, that Q sub F factor accounts for the global utilization of that HSS column. So as that column sees compression and flexure, depending on how highly stressed that column is, will determine what Q sub F factor we need to apply. So if that wall is highly stressed, and then if you imagine trying to punch in something into it like a plate, then you'll have less strength there to resist it. So we need to make sure and account for that. There are a couple more limit states to check for that vertical stiffener plates that's listed here. We have minimum stiffener plate thickness based on the thickness of our joist stem, and as well as our weld size of that stiffener plate to the HSS column. We also have to look at manual table 10-8 for the width of the seat plate. There is a full worked out example in STI Manual Volume 3. So the STI has developed design guides for HSS. And if we turn to Volume 3 of those design guides, example 3-5.6 has a full example of a stiffened seated connection to an HSS column. Next, we have the bottom chord connection to design. We have stabilizer plates as shown here at the bottom chord of the joist. Generally, there is a 1-inch gap between the double angles at the bottom chord and the HSS column. And so a 3/4-inch plate is typically where you want to start for that stabilizer plate, even if you find that you may not need it for strength. That 3/4-inch plate is nice because it allows that bottom chord to slip over during erection, and then we can fill it weld right to that plate. Usually it's being limited, that plate design is limited by wall plastification. That's usually what controls, unless we have reinforcing plates in the HSS column to help with the flexural capacity of that column. So we turn to the STI limit state axial table, the longitudinal plate connection type, and there we see that we need to check for plastification of the HSS. As I mentioned, this is likely to control for an unreinforced HSS column. We use equation 9-44 of the 16th edition manual, which is based on the image you see here on the right, plastification of the HSS wall due to an out-of-plane transverse load. So we go through and we substitute our variables in. C will be equal to the thickness of the plate, and L is equal to the vertical length of that plate. If you are more familiar with previous editions of the specification, I listed the equations that this classification equation is equivalent to down below for your reference. If we provide reinforcing to that tube wall, as shown here is an example of that in the image on the right. So with reinforcing, wall plastification will no longer control. And there are two limit states that we need to check, which are sidewall crippling and local yielding of the sidewalls. To do these checks, the specification points us to Chapter J. So for wall crippling, we use equation J10-4 with the substitutions listed here for that HSS wall sidewall. And for local yielding of the chord sidewalls, we use equation J10-2. I wanted to note that if you do end up reinforcing your HSS, I encourage you to look at resources on the STI website, which I have listed at the end of this video for designing that reinforcement to the HSS column. This stabilizer plate connection, again, we want to think about this when we're sizing the HSS column and designing that HSS column. We want to think about that wall thickness. As you can see, there were a few limit state checks that we needed to make that includes that HSS thickness in the equation. It's best to perform these while you're still in member design before bid, and specify a thicker wall if you need to in order to take those connection forces. In general, when we're sizing HSS connections, it's better to have a thicker wall, even though that will drive our tonnage up a little bit more, because upsizing to a thicker HSS wall is almost always going to be less costly than having to add a reinforcing plate to the face of the tube and welding it. Likewise, it's also going to be more efficient for me to increase that wall thickness rather than specifying a through plate, where a fabricator has to slot the tube in two walls and then provide a weld on both sides of that through plate. So for your joist to HSS column moment connection design, I've listed a few resources here as you continue on with that connection design. As I mentioned, we have design manuals, and there are 4 volumes. Volume 3 has a stiffened seated connection that would be helpful for you in your stiffened seated connection design. Dr. Packer wrote the article on branch bending for your moments in plane bending capacities that I listed. And for reinforcing your HSS, there are 2 resources. Dr. Packer wrote an STI article as well, and there is a webinar on demand recording that steps through this in more detail. SJI also offers resources for designing the moment connection for the plates and the weld designs. They have a spreadsheet as well as a reference manual and a user guide to that spreadsheet. The Steel Tube Institute has several resources for designing your HSS connections. I wanted to also highlight HSS Connects, which is a web-based tool on the STI website that is free to access to help check the adequacy of your HSS wall at connections, and we highly recommend doing this for the reasons I mentioned in this video to avoid reinforcing your HSS or having to upsize after bid. This is a list of several design resources for your HSS projects. STI has a resource library of technical articles. We also have a capability tool to help you find available HSS sections for your projects. I discussed the limit state tables, design manuals, and HSS Connects in this video. We also have spreadsheet tools, as well as live webinars and free past webinar recordings that are free to access on our website. We have e-news, emails to stay up to date with HSS resources and webinars. And then finally, we have professional membership for individuals and offices to offer 6 live webinars per year, a discount on HSS design manuals, access to spreadsheets, and more. Thank you very much for taking the time to join this video. The Steel Tubes Institute's goal is to be your trusted resource. We're happy to assist with any design needs that you may encounter on your next HSS project. Feel free to visit our website where you can sign up for e-news and send us any questions that you may have. Thank you very much.